recognize the reaction is pretty simple, right? You get the alkyl halide, you're reacting with a nucleophile. What happened? The halide replaced by the nucleophile, right? There's a nucleophile there. So if you recognize the nucleophile right, all you need to do is replace that. So this is a nucleophile. So again, what's a nucleophile? Species that has a high electron density. It is an electron that makes it work. So which part of this molecule has a high electron density? Not the hydrogen, not the carbon, right? The oxygen. Oxygen is negatively charged, but the negatively charged means it has more than what it used to have. That's why it's negatively charged. So that oxygen is going to make the attach this carbon, and then halogen is going to be released, as we saw in the mechanism in the previous slide. Then you're going to create this bromine replaced by the nucleophile. So you're going to create this molecule. It's very simple mechanisms and very easy to write. What I don't want to see, a lot of people does it by the way, is this. They don't thought about which part of the molecule you populate. They thought that the whole thing comes, replace that, is a pretty like this. That is wrong. Because you don't recognize the nucleophile right. I mean, sometimes people just using only the potassium hit it, and the bromine blue comes out, and then you've got the K there, not the other one. Then it's not right either, right? Because the potassium is a positively charged cation. Positively charged cation doesn't seek for another positively charged carbon, right? That's the same charge. They should repel, not get attracted. So I know this is a very simple job, but if you don't think about it, you're gonna still get the wrong answer. So I want you to know why this thing happens. Nucleophile seeking out the electrophile, especially the electric being sent. These nucleophile attack not this carbon, right? Because this carbon has a full share of the electrons in the carbon. So there's no electron deficiency in this carbon. Only carbon that has electron deficient is this carbon, all because of the halogen there. So I want you to understand why things happen this way, and then where it happens, what comes, right? What becomes a part of the products. So we do look at things very carefully. I mean, this and that, just one letter there or not, somebody can argue that, yeah, that's about 95% same, you should give the 95% of the credit. And I'm going to say, no, you did this because you don't understand the concept. You get zero. So you really have to understand why this thing happened. And that shows when you're giving wrong answers. This is an oxygen negatively charged as a nucleophile. That nucleophile can be a carbon nucleophile. This is a triple bonding carbon negatively charged there. And that's the one can make an attack to this carbon, same as before. And then that will kick the halogens out. And then that makes a new product. So that's also the SN2 reaction. So I want you to understand what is a nucleophile, which part of the nucleophile, and then where it's going to make an attack, right? The carbon bearing the halogen, not any carbon. Right? They don't do anything in random. There must be a reason why they do that. So that's the thing that you need to understand. Sometimes you have to understand that we can ask the question in other way. Yes, we can give you the study material and reagents, and then we can ask you to predict what's the products. Sometimes if we ask you to, if you want to make this, then what you're supposed to have beginning. So you can have to look at things in the multiple different directions. So which is not too difficult if you know that you can create a bond with a nucleophile with the alkyl halide by the SN2 reactions. So you can imagine that you can probably make this bond by the SN2 reactions. By the same manner, you can also make this bond by the nucleophilic reaction as well. So we can have potentially two different right answers. So one of them is basically, if you're recognizing, I mean, this is going to be made, you got oxygen belong to this part of the molecule, that becomes a nucleophile. And that part has to be the alkyl halide, so we have to put the halogen there. So when the nucleophile makes an attack, hello to leave, then we can create this bond. So that is one way to make this molecule. If you want to make a molecule in another way, by considering making this bond, then these substrates belong to that part. So that part needs to be the nucleophile. And then this part has to be the electrophile having a bromine there. So you can nucleophile makes an attack and the bromine comes out, so you make a bond there, like SN2 reactions. So there's a two different ways possible. And these two is kind of equal, but not always. Sometimes there's some more favor than the other, something that you need to be able to figure out, but which we'll be discussing later. If you want to make this bond, you can see that we don't normally try to make this bond because carbon bond created by this, you need to have a carbon the bromine here or chlorine there. That's fine, but the carbon being a negative charge, which is not very stable. Carbon is really strong, it's unstable. So something, that's what makes it difficult. So what's the best way to make this one? Consider making this bond. So you got the alkyl halide there, and then you got the amine comes as a nucleophile. Why the amine was chosen as a nucleophile? Amine is a lone pair. The pair of electrons there. That can be used for the seeking out the electron deficient carbon. So that is a pretty simple way to make a bond by kicking the bromines out and make this bond. So these bonds are much easier to make than get this bond and that one, this one and that one. So there's just some easier one and more difficult. I'm not saying that it's not possible, it's really, really difficult. We see the hydroxide come there to replace the bromine. So will this replace that and make a bond there? Or will that come here and make a bond there? Which one is better? So what this question is asking, which one is a better nucleophile? Really again. Is this a better nucleophile, or that's a better nucleophile? What is the governing concept there? Is electronegativity, it's the size, and what being more polarized, right? That's a better nucleophile because it's a less electronegative and it's a bigger, right? It's a more polarizable. So that comes out, makes an attack much easier, so you get this, not the other. What will be the products of this reaction? So what makes it nucleophilic is a nitrogen lone pair. This nitrogen is lone pair, that nitrogen is lone pair. So which one will be most likely a good nucleophile? This one or the other one? That's how you just think it. This murky alkyl chain makes it less nucleophilic because you got this body, think about that. You got a huge things coming around with you, and it's really hard to fit the small space of the carbon and keep things. But these ones are much more small and agile. So it can hit it, even though it's less powerful, but it can hit it better because it's more accessible. Can you tell me which one is going to be better for the SN2 reaction? This one or that one? Now, you're going to see that this is a high iodine on this carbon. This carbon can be classified as a primary, secondary, or tertiary. This carbon I'm talking about. This carbon has just one carbon chain. That might be big, but this is just one. That's a primary alkyl. This one, on the other hand, that one has a 3 carbon chain. That's a tertiary alkyl. So there's 2 working for the substitution reaction. So that one is a better SN2 reaction substrate than the one. Between these two, same thing, right? That bromines on the 2 carbons, the secondary alkyl. This was a tertiary alkyl. The secondary is better than the tertiary, so this is what it is. Then there is a very popular exception. Compared to between these two, which one is a better SN2 substrate? If I'm asking you, then you're going to see that this is iodine under this carbon. That carbon has just one carbon directly bound to it, even though it's p-butyl. So you may consider that as a primary alkyl halide. That one, iodine is on the secondary alkyl halide. Primary is better than the secondary. So this should be better substrate than the other one. But this is a p-butyl. That's the thing. P-butyl just becomes too big. If that iodine is on this carbon, on that carbon, that's becomes a tertiary halide, that are bad things. But this was a primary. But this primary had P-butyl right next carbon. P-butyl, the presence of P-butyl goes a little further than you think. If even is 1 carbon away, that huge thing still makes a problem of the nucleophile approach this way to hit the iodine. So even that's it's worse than the secondary iodine. If I put another chain, P-butyl 1 more carbon away, then it's not having that presence. So that becomes a primary aldehyde. We get the better SN2 reaction with that. But if you got the primary, but the P-butyls at next position, tertiary positions at next, quaternary carbons on next carbon, then this is not a normal primary aldehyde. That's even worse than the secondary. So this is kind of exceptional cases, but it tells you that steric hindrance, sometimes it actually makes a bigger presence, sometimes it carry over 1 more bonds away because just being too huge. So I want you to pay close attention to this exception here, because of this being asked a lot in the test. All right. Couple of questions that we're going to solve and then probably then turn it up. Oh no, you got 6 minutes. Let's check the time. Well, we got a lot to talk about, right? Remember that. So let's think about what products you're going to get. We got 1 nucleophilic point, so that's the nucleophile, the main nitrogen there. But if you look at the halogen here, we got the bromine here, so it can happen this carbon, and then kick the bromines out, or it can happen that carbon, kick the chlorines out. Which one is most likely to happen? So this is based on the concept we just talked about. The Berkey aldehyde, not a good SN2 reaction, right? Steric hindrance. Which one is the less sterically hindered? That one. So reaction should happen to this one a lot faster than the other one. It's all because it's less sterically hindered. What about this one? That's a secondary aldehyde. If you look at this chlorine, that has only 1 carbon chain there. That should be considered a primary aldehyde, right? So then this one kick this one and kick these chlorines out. Yeah, someone remember. I've been telling you, halogen on double bonds, not the subject of the reactions at all. They don't get substituted by the SN2 reaction. That's why I stressed it out so many times in the beginning. I stressed even today. I've been showing you. This is not getting replaced because the double bond with the carbon right there. So you gotta know what you're gonna be reacting with. That one is a secondary, at least it can go. Tertiary, probably no reactions. But at least secondary can happen.